Okay, let's see. We started talking about bipolar junction transistors. Okay, in bipolar junction transistors, we came so far as to analyze the DC and do the DC analysis using different operating condition and finding out the operating condition. Now, a quick correction. In the last class, when I was writing the notes, I mentioned IC is alpha times IE. It really is IC over alpha gives you IE. Okay. Alpha is a number that's close to 1. It's roughly in the range of 0.99. Okay. That's something we want to remember, beta by beta plus 1. Okay. We started looking at this, and then if I have to write the general steps, okay, the general steps that you would follow for any problem. Okay, here is a PNP transistor, right? The first step is to notice that VBE, and in this case VEB, is 0.7 volts because of the forward biased diode. Okay, when we know the BJT is operating in the active region, you can pretty much assume VEB for a PNP and VBE for a NPN to be 0.7 volts. Okay, once we know this, the next step would be Ohm's law. We know the voltage on one end, and we just found out the voltage on the other end. So we should be able to calculate IC using Ohm's law. Okay, once we calculate IC using Ohm's law, beta is given to be 100. If nothing is given for beta, you assume the value of beta to be 100. Okay, so here is the underlying idea. If you have beta and 1 current, you should be able to calculate the other 2 currents. Okay, you can find that out. Or if you have beta and IE, you can calculate the other 2. Okay, so once you know the current gain factor in active region, I should be able to calculate IE as IC over alpha. Well, alpha is simply beta by beta plus 1. So the third step is using these two, beta and IC, to calculate IE. Okay, once I have IE, again, the fourth step is the application of Ohm's law. Okay, I have the voltage on one side, I have the current flowing through this, so I should be able to find the voltage on that guy. Okay, I should be able to calculate VE or VC, sorry, VC collector. This is PNP, right? VC, find the value of VC. Okay, once we find the value of VC, now it's a matter of finding IB. Fifth step is simply finding IB from these two. Okay, I have IC and I have beta. Divide IC by beta, you get IB. Okay, so the relationship is pretty simple. We didn't even get to apply the exponential equation here. Okay, all we did was simple Ohm's law and then the usage of beta. Okay, DC analysis is more or less straightforward if you can tactfully use the information that you have to arrive at the information that you need. Okay, this is how far we came along. And then the important point for us to consider is that we should get enough practice with these problems that we are able to do all of the analysis on the figure itself without having to replace the BJT with its equivalent large signal model. Okay, we don't want to have to do that. Okay. Then here is another problem. We want to analyze this circuit in figure 6.28a to determine the voltages. You remember, analysis means that all the device values, component values are given to you. You're expected to find V, E, V, E, this guy is VC, V collector, V base. Okay, so, and then of course, I collector, I emitter, and I base. Okay, this is what we are asked to find out. By analysis, we are expected to find out all of these values. Okay, if we find V, E, VC, VB, and IC, IB, IE, then we can call our analysis complete. Okay, let's see where we can begin. The idea is simple. I want to look at this voltage division circuit and see if I can represent it using a Thevenin's equivalent. Okay, Thevenin's equivalent simply is voltage division circuit RB2 over the sum of these two. That's the equivalent resistance. Okay, 5 volts. So RBB, the equivalent resistance that can replace the parallel combination, is that guy RB1 in parallel to RB2. So the V Thevenin is this guy. The R Thevenin is this guy. So what I have simply done is to replace this voltage divider using its equivalent resistance and Thevenin voltage. Okay, so that's all we have done here, just so we can write a loop equation around it. Okay, then what? Then we have to evaluate the base emitter current. We want to write a loop equation around the loop over here. Where's the loop? There's a loop over here. See, there is plus or minus 5 volts. Because remember, that's this guy is supposed to go to 5 volts. Okay, so this 5 volts is right here. Okay, then we have a loop. When we write the loop equation, KVL around loop L. Okay, so all there is begin at the lower left and follow a circular path. So this voltage negative 5 volts should equal the voltages dropped around these loops. So the sum of these voltages, okay, so this voltage VBB, that's the voltage that we are applying here, 5 volts, should equal the sum of voltages dropped in these two resistances. And of course, there is a plus minus 0.7 volts over here. Let's not forget that either. Okay, so when we write the loop equation over here, there are 3 components. There is this VBB, that's VBB. So the voltage dropped across this guy, okay, the voltage dropped across this resistance, that's shown using IB times RBB. Then let's not forget the voltage drop between base and emitter, okay, that's VBE voltage. And then there is, of course, the voltage dropped in the resistance 3 ohms over here. Okay, all of that value should equal the applied input voltage, which is 5 volts. Okay, the input applied voltage is 5 volts, so that's VBB. So when you write the loop equation, the voltage supplied is equals to the voltage dropped. Okay, so using that, I can find VB. Okay. So now that gives me IE, okay, which gives me IE to be 1.29 milliamperes. 1.29 milliamperes. So all I have done is to replace this guy, IB. I don't want two unknowns. I want to eliminate IB and express it in terms of IE. Okay, so what I have done is wherever I find IB, I'm going to replace it with IE by beta plus 1. Okay, so this guy, RBB by beta plus 1 is IE. So that is coming there because I have factored out IE. So RBB times IB is RBB by beta plus 1 times IE. So that's the idea that corresponds to the purple part shown here. And then there is a RE term over here corresponding to the green RE term. And then there is, of course, the VBE term, that's the blue term, and then the VBB term. So as you can see, all I have done is simply rearranged the equation and then expressed IB as a function of IE and beta. Okay. Once I do that, I get a value for IE. Okay. Once I get a value for IE, okay. Once I have the value for IE, of course, beta value is given, right? So I should be able to calculate IB. Okay. See, IB is, remember, IB was substituted to be this guy. IB is IE by, cancel that. IB is IE by beta plus 1. Beta is 100. IE is 0.129. Beta plus 1. So I get a value for IB. Okay, IB is that guy. Once I have IB, I should be able to find the value for VB. Okay, if I have, so this guy is 0, this guy is 5 volts. The voltage on one end is 5 volts. Okay, and I know the voltage is the voltage on this node. Let's see the voltage on this end. Okay, let's see. If I know the voltage on that end of the resistance, then I can simply apply Ohm's law. Okay, in order to find VB, okay, VB, that's the voltage here. That's going to be the voltage that is applied at this node, which is IERE plus 0.7 volts. Okay, VB is simply V emitter plus 0.7 volts. Okay, as you can see, VBE is 0.7 volts. So VB minus VE is 0.7 volts. Therefore, if you wanted to find VB, all you have to do is 0.7 plus VE. That's all you are doing here. So this guy is VE plus 0.7. Okay, so that's the idea. Once you calculate that, once you calculate IERE, which is VE plus 0.7, you have a value of 4.57. Okay, 4.57 for this guy. So VEB is 4.57, and this guy is not surprisingly 0.7 volts below that. Okay, as a matter of fact, we calculated this guy first and then added 0.7 to that to get a value for VB. Okay, once I get a value for VB, I can move on to calculating the IC current. Okay, IC current again is simply alpha times IE. Okay, alpha times IE. Remember in the last problem, we calculated IE using IC over alpha. Okay, and alpha is nothing but beta by beta plus 1, which should be close to 0.99. Okay, so using that, I can calculate IC to be 1.28 milliamperes. Okay, now once I have IC to be 1.28 milliamperes, not this guy, once I have IC to be 1.28 milliamperes, I should be able to calculate the voltage at this node VE or VC, sorry, the voltage at the node right here, VC, is 15 volts, the power supply, minus the voltage dropped in the resistance. Okay, as you can see, the voltage at this node is power supply minus the voltage dropped in this resistance. Okay, 15 volts minus IC into 5 kilo ohms, if this is IC. Okay, that should give me the voltage for VC. When you calculate that, it comes out to be 8.6 volts. Okay, 8.6 volts. Okay, as you can see, the collector is at a higher potential than base by 4.3, which means that the transistor is in active mode. Okay, and we can verify the validity of our assumption. Okay, to get a stable bias point where beta varies, independent of beta varies, it's a good idea to set the bias not using one resistance, but using a good idea to set bias current through a base bias resistances. Okay, like not just one resistance here, this is a bad idea, but instead you get the same effect using a pair of resistances over there. Okay, so by using this approach, what happens is the gain becomes much more stable. The current in the BJT is much more resilient, much less volatile to changes in beta. Okay, in the last class I also mentioned how addition of this additional resistance in the emitter, this is called degeneration. Okay, by using a degeneration resistance, I mentioned that there is an inherent built-in mechanism that counteracts any sudden changes in IC and IE as a result of significant beta changes. Okay, that's the idea of degeneration. To get symmetric output voltage, it's always a good idea to bias VC about halfway between base bias voltage VB and the positive power supply. Okay, so if I have a positive power supply of 15 volts here, and this guy is going to be 5 volts, you want to make sure that you're biasing your C just so there is enough voltage headroom. So this guy is voltage headroom requirement, just so when you're amplifying your signal and you get a pretty big swing on the upside, swing to the upside, then you're not saturating your at the power supplies. Okay, you want to make sure that you're choosing your operating point such that there is enough voltage headroom. Okay, other questions, please? Questions? Okay, all we have done here is to simply do KVL. Okay, Okay, once we have KVL, the direct result of that is right here. And in order to simplify the equation, we just had to use beta. Okay, KVL in conjunction with beta gave me the value of IE. That's all I needed. Once I have IE and beta, I should be able to calculate IB. Once I have IB and once I have IE, I should be able to calculate VB, the base voltage. Okay, base voltage. Um, and then once I calculate the base voltage and using the IC and alpha, okay, IE and alpha, I should be able to calculate IC. That's all there is to it. So this is all DC analysis. This is all DC analysis. Okay. Now let's move on to doing the small signal analysis. We did not get a chance to spend a lot of time on the small signal model of MOSFET, which is in some sense similar. We did not talk about it, but if you were to do that, if you were to spend some time on MOSFET BJT, what am I talking? On MOSFET small signal model. Okay, if you apply a voltage of V in, there is a GM V in current source, and then there is R naught, which is 1 over lambda ID. So the bottom line I'm trying to drive home is that excepting for this additional resistance, the small signal model for MOSFET is pretty similar to the small signal model for BJT. Where is this resistance coming from? This resistance is coming from the fact that this is a forward biased diode. Okay, this is a forward biased diode with a potential of 0.7. If you remember, go back to diode. If I go back to diodes, let's see. Look at the small signal model for a diode. I don't know where it was. I may have to do a little bit of searching around, but then it looks like we are heading in the right direction because I see the small signal model for diode right here. Okay, the small signal model for a diode is simply a resistance. Okay, small signal model for a diode is a resistance. So this circuit, all of this circuit is equivalent to having this diode replaced by resistance. Okay, so when it comes to small signal model, that's exactly what I'm doing. The diode that was supposed to be here, the diode that was supposed to be here has been replaced by its equivalent small signal model, which is the resistance. Okay, the rest is a dependent current source. It's a dependent current source. The VBE, okay, the VBE generates some current. Okay, let me go back to the equation really quickly. The current in the collector, current in the collector okay, please bear with me for a minute while I go back to the equation here. IC is this guy. Okay, let me copy that. I'm going to come back down here. Okay, and I'm talking about the small signal model. Okay, okay, this is the expression for BJT. Okay, so pay attention to what's going on over here. This BJT, the current in the collector, okay, the current in the collector is a dependent current source. It depends on VBE voltage. That's exactly what I'm doing here in this case. The current is a dependent current source. Okay, so if you see there is no relationship, or if you don't quite readily see relationship between this equation and the small signal model, well, you have to realize that they're fundamentally the same. Okay, there is a current source IC that depends on the value of VBE. That's what I'm doing here in a schematic manner. I have a current source whose value is dependent on V pi. What is V pi here if it's not the voltage between VBE? So VBE, this is not capital VBE, which is 0.7 volts. Okay, so this is the signal that is riding on top of the DC bias. Okay, so this is a small, teeny tiny voltage signal that is riding on top of that DC signal. So this is little VBE, is the small signal model. So when I change the input voltage, VBE, when VBE is changed, corresponding to that change, there is going to be an IC that is changing. Okay, and then in order to take care of this guy, 1 plus lambda VCE, okay, I incorporated a resistance R naught. Okay, R naught is 1 over lambda IC, remember? So this represents the channel base width modulation, okay? And then the dependent current source really represents the action of the transistor, okay? The current in the collector depends on the base emitter voltage, and that is represented in the model. That is captured, that behavior is captured in the model using a dependent current source. Okay. Now, of course, V pi is IB. If the current flowing into the base is IB, that's Ohm's law, IB times R pi. Okay. And beta is the current gain factor, right? Beta is the current gain factor. So I could have written this as beta times IB as well. Okay, I could have written this as beta times IB as well. Remember, because the IC is beta times IB, right? So by the same relationship, I could have expressed this as a current source that is dependent on this voltage, or I could even express it as a current source that is dependent on the current. Okay, so that's the idea. So I'm expressing BJT as a current voltage voltage controlled current source, and in this case it's a current controlled current source. Therefore I use a current gain factor beta. Okay, this is called a hybrid pi model. This is called a hybrid pi model. And then remember these terms for GM, the transconductance, which is IC over VT. Okay, GM is defined as the change in IC for a change in VBE. Okay, when you evaluate that, you will see that it is IC over GM by definition is how much is the output collector current changing for change in for a small change in VBE. That's the definition of GM. When you evaluate that, when you do the derivative of e to the x is e to the x. The integral of the e to the x is also e to the x. That's the only wave. Exponential is the only wave in the universe for which the derivative and the integral are the same as the waveform itself. Okay, that's the reason why when you evaluate delta IC over delta VBE, there is still some IC term in that derivative term. okay, GM. So IC over VT, which is IC over KT over Q, okay. So GM can be evaluated if you have IC and VT. So the GM is a function of the operating point of the MOSFET, or the bias point, or the quiescent point. Okay, so now there's also R naught, which is 1 over lambda IP. We calculated this over and over and over again. R naught is 1 over lambda IC. Okay, 1 over lambda is VA. Okay, that's all something we discussed in the last class, didn't we? Let me go back and show you, maybe if I can recall the similarity between BJTs and, okay, so here R naught is VA over IC. So this is something we are familiar with. Okay, let's see. Okay, now, so this is the small signal model. I could use either of these models interchangeably, depending on whether I want to use a voltage controlled current source or a current controlled current source. Or in other words, if I want to make use of GM, I would use this guy. If the beta value is not given, I would use this guy. If the beta value is given, it's not quite often that you find beta value not given. So when the beta value is given, I can calculate the beta IP current over here. So this guy, GMR naught, is called the intrinsic gain, or the maximum gain that we can get out of this BJT amplifier. Okay, as it turns out, for most transconductance amplifier, if I were to, so I should really be writing this GMR naught over here. Okay, so if I connected a load resistance over here, RL, okay, the gain would be GMR naught in parallel with RL. So the gain has fallen. Okay, the parallel combination R naught in RL, R naught in parallel with RL is less than R naught, always a parallel combination. So in other words, any load that I add, it adds to RL in R naught in parallel. So anything that is added in parallel reduces the overall output resistance, therefore the gain comes down. The maximum gain that you can get is when there is no load resistance connected. Okay, therefore the gain of this guy is GM R naught. Okay, GM R naught is the gain, the intrinsic gain, or the maximum gain that you can get out of this. Okay, here is the BJT as a voltage amplifier. This is your teeny tiny input. Okay, this is your teeny tiny input. Corresponding to that, the output is going to swing quite significantly. Okay, the ratio of the peak to peak voltage between output to the input, that gives you the gain. Okay, BJT amplifiers can be analyzed using a standard linear analysis technique for small signal variations around. So typically the idea, let me mention this idea. Let's say I have y equals to x squared. That's not a linear relationship, right? A non-linear relationship. Okay, I want to talk about the idea of small signal model, approximation as a linear circuit. Okay, so really, if you remember the idea of MOSFET or anything that is not linear, this is non-linear. okay, behavior where X is the input, Y is the output. What I mean by nonlinear is if I add a value to X to the input, then the output is not. So Y output is superposition that does not apply. Y output is not the same as Y output for. So here is the idea. So let's say Y1 is X1 squared, Y2 is X2 squared. Okay. If the input was not X1 or X2, if the input is a linear combination, then Y3 is not the same as the individual uh, responses, Y1 and Y2 response. So that's the idea of linear, non-linear behavior. Okay, non-linear meaning that when the input changes, the output does not change um, by the same using superposition. Okay, so here is the idea for this y equals to x squared. So if you know y1, if I change this x to be x plus delta x, a small value of x, then y2 is going to be, so x2 is x plus delta x, x1 is this guy, okay? Then y2 will be x1 squared plus delta x squared plus 2 times x1 times delta x. Okay, so that's the idea of so this is the idea of y2 in response to an increase in delta x. So my argument is, and here is the argument that we will make for all the small signal analysis. If delta x is small, if delta x is very, very small, I can make the assumption that delta x squared is 0. Okay. Now, therefore, y2 is x1 squared plus 2 times x1 times delta x1. Okay. So we have eliminated the um, teeny tiny x1 squared. So the idea is this component. Okay. This component is called the DC component. Okay. The unchanging DC component, because that is common to this guy and this guy, y1 and y2. There is some term that is common in when the input was x1 and the input is x1 plus delta x. In both of these cases, there is a component, common component, x1 squared. Then there is another term. So what I can do is this response, this is called the AC or the small signal response. So what we have done is what is essentially a non-linear behavior. Okay, this squared law dependence, we have broken that with the assumption that this is very, very small. So the assumption that we can use the small signal model is predicated on the premise. The premise is that the small signal, the VBE signal that we are applying here is really small in comparison. And that is shown here, that VBE is really small, so as not to change the operating point much. Okay, when we keep the VBE small, the resultant output voltage is going to be gain. There is going to be a gain in that guy. Okay? Not only is there a gain, there is also the gain is inverted owing to the fact that the transfer curve has a slope that's not 1. Okay, that's negative. It has an inverse slope. It has a negative slope. The transfer curve has an inverse slope, The slope represents the gain at that point. Okay, so when the slope represents the gain, what happens is the inverse negative slope means that there is an inverting amplification going on here. Okay, some of these things may not be discussed in the textbook, but the idea, you'll see this over and over and over again. All you want to remember is when you are using a small signal model, what you're doing is you're evaluating the response, you're breaking it down into a DC component and a linearized a small signal time varying component. Okay, so meaning that there is a DC component like so, which corresponds to the unchanging in the three scenarios. And then there is a linear component, which is not squared law dependence. This is linearized, meaning that we ignore the higher order component. We ignore this guy, the x squared term or any other term, because that is a small value. Okay, that's a small signal model, meaning that there is a DC and an AC component. So if you look at this circuit here, so there is a DC term here, okay, which I had shown earlier using the blue highlight. And then there is a small AC term here, okay. Even so, so that represents the DC term over here, and a small change in the input. So here is capital VBE, and there is this little VBE. Okay, that's exactly what we are doing here. I'm adding a small time varying signal, this guy, on top of a constant DC signal. Okay, if I were to show this graphically, what happens is on the at that VBE, constant DC value of VBE, I'm applying a small little VBE term on top of a capital VBE, okay, the DC term, and I'm superimposing a small AC term on top of it, okay. So given if the AC term is small, we can linearize, meaning that we can simply ignore the higher order terms, okay. Okay. Now, how would you solve a BJT voltage amplifier problem? Okay, the voltage amplification problem simply is, like I mentioned, the whole idea of a small signal model is you can break your analysis into the blue part and the green part. Okay, blue part we are already very familiar doing that. The DC, this is called the DC analysis. Okay, and then we want to do the AC analysis as well, AC analysis. Okay, by linearizing, what I mean is the argument goes, if the AC signal is so small, then what is supposed to be a non-linear relationship can simply be converted to a superposition. Okay, that is what the general procedure involves when you do the analysis. Okay, you first do just the DC analysis without AC. VB equals V little b equals to 0. Then you do the AC analysis assuming VBE is deactivated. So there are two terms here. There is a signal term shown in small letters, and there is a lowercase letters, that small signal AC, and there's a capital uppercase letters, which is the DC analysis. Okay, make that observation here. If you observe, the DC values, the large signal values are are shown using capital case, uppercase, and then the small signal values are shown using the lowercase. The resultant is this guy, VBE, which shows the overall effect of both of these on this signal. Okay? So the analysis is simple. The application of small signal equivalent is simple. What we do is we first do the eliminate the signal source and determine the DC operating point. So we do the large signal analysis. So the underlying scheme is this guy, is the application of superposition. Okay, we first do the DC analysis. Okay, we do the DC analysis and calculate the node voltages, node currents, all the VB, VC, VE, IB, IC, IE. That's the DC analysis, right? Once we calculate that, we are in a good shape to calculate these parameters, GM, R pi, which represent the marriage between the DC and AC analysis, okay? Once we find out R naught, GM, and R pi, the small signal model parameters, then we are in a position to write the small signal model, okay? Once we find out GM, R pi, and R naught, they're dependent on the DC operating conditions. Once we do that, we are able to write the small signal model. Then what we do is DC analysis, no AC, okay? Then what we do is we do the AC analysis, okay? Assuming that there is no DC value. Okay, assuming that there is no DC value. So I'm going to show you an example right here. Okay, and then replace BJT with one of its small signal model, analyze the resulting circuit to determine the required quantities. Okay, so let's do an example. Let's do the illustration using this example. We wish to analyze the transistor amplifier to determine the voltage gain. Okay, so when you see this kind of a problem, voltage gain, okay, then it means you have to do the DC analysis and then do the AC analysis. Okay, voltage gain, that is the output voltage over the input voltage. What's that gain? What's the output voltage over the input voltage? Okay, the small signal gain, the little VO over little VI. In order to do that, we have to start by finding the DC analysis. So the first step to do is, what's the idea of superposition? The first step in superposition is that you can independently find out the response of this MOSFET, the response of this BJT to just the DC component, okay, not the AC component. I'm going to make the AC signal 0, okay? Just look at the DC signal. That's what I'm going to do here, okay? So by that argument, what happens is this 3 volts is right there. And then I can find out the node voltages and node currents. As a first step, what I want to do is to notice that this voltage is 0.7 volts, okay? Because the emitter is ground, base comes out to be 0.7 volts, okay? Once that is 0.7 volts, I should be able to calculate IB, okay? IB is simply 3 minus 0.7 by 100 kilo ohms, Ohm's law, okay? The voltage on either sides of that 100 kilo ohm resistance, okay? 100 kilo ohm resistance to find out IB value, okay? Once I have IB value and beta is given, what I can do is multiply this IB value with beta to get IC, okay? So that gives me an IC value of 2.3 milliamperes. Once I have IC value, I should be able to calculate VBE, C, which is 10 volts minus the voltage drop across the 3 kilo ohm resistance. Okay, so that gives me a value of VC to be 3.1 volts. VC equals to 3.1 volts. Okay, now what I can do is this voltage is 0. Now in order to find I emitter is simply I collector over alpha. Okay, I collector over alpha. Once I do that, I should be able to. Now this is a complete DC analysis because when I mean DC analysis, what I simply mean is what's the value of VC over there? Well, that's 0. What's the value of VB over here? That's 0.7 because it's a forward bias, one end of the forward bias diode. And what's the value at VC? I found out that the value at VC is 3.1 volt. Then the next step is, so we found VC, we found VE, we found VB. We also found IB, found IC, and IE. So that determines my large signal DC analysis. Okay, so that's the step number 1 here. Eliminate the signal source and determine the DC operating point. Okay, the DC operating point is simply the values for this. Okay, DC operating point is the values. When somebody asks you to find out the operating point, what they're asking you to do is to give us the values for all of these terminal voltages and branch currents. Okay, good. Now it comes down to the next step would be to talk about to calculate the small signal parameters GM, which you can calculate from IC. Okay, you can calculate R pi from GM, and you can also calculate. So the next step is in calculating. Okay, we don't talk about RE, the hybrid T model, but that's fine. So we calculate GM. The next step is to calculate GM, R pi, and R naught. Okay, so these are the small signal quantities. So once you did the DC analysis, before you can do the AC analysis, you have to find out GM, R naught, R pi. Okay, these quantities represent the union or marriage between the DC analysis and the AC analysis. And then there, all you have to do is plug in the numbers. You know the value of IC, so you know the value of VT, calculate GM. Similarly, beta value is given. Okay, GM, you found out GM value in the earlier step, so you can calculate R pi. Similarly, where is R naught? We can simply calculate R naught to be 1 over lambda ID. Okay, but let's see, there must be some hint provided in here. Okay, to ask you to ignore the base width modulation. If you're asked to ignore the base width modulation, you can ignore the R naught over here. Okay, R naught can be ignored. The base width modulation can be ignored. Now, once you do that, what you have done is simply use this value of R pi. Okay, you can plug that in here, right here. Okay, that's right there. That's R pi. This GM, that GM can be used here. Okay, and then remember this RC, the external capacitance, is connected on the load. Okay, 3 kilo ohm resistance happens to be the load. Now we do the AC analysis. So AC analysis. is simply to eliminate the DC sources. And that's the reason why this VCC is tied to ground, because I wanted to deactivate the DC source. The way to deactivate a DC voltage source is to short circuit it. A DC voltage source. For a current source, if you want to deactivate a current source, you simply open circuit it. Okay, so that's one mechanism. That's the way to deactivate DC sources. So you can do the AC analysis just by itself. So remember, all I have done is there was a capital VBE over here, right? I simply deactivated it by replacing it with a short. Okay, similarly, there is a VCC over there. There was a VCC over there. Okay, there was this VCC term over there. Okay, in order to do the AC analysis, what I want to do is to tie this to ground. Okay, we want to tie this to ground to deactivate this, and that's the reason why you see that going to ground. Okay, so now you can rewrite this small signal. This circuit is now ready for small signal analysis. So I replace this BJT with its small signal model. Okay, I replaced it with its small signal model. Now this RBB is coming from outside this circuit. Okay, that's this guy. RBB is 100 kilo ohms. It's an external resistance that we connected. Similarly, there is this RERC, that is the external load capacitance that we found. Now it's just a matter of calculating the signal loss and the gain over here. So we are interested in finding out V output. Okay, and we are interested in finding out V output. You know, the current flowing here is, this is plus and this is minus. So if a current of GM is flowing in this direction, GM VBE is flowing in this direction, okay, then the voltage would be, V output would be negative GM VBE, okay, because that's the passive sign convention. Okay, negative GMVB. So all you want to remember is simply how much change in input causes what change in the output, V output. Okay, so you're interested in finding out the relationship between, finding out the expression between V output and V input. Okay, that's what you're after, because that's gain, right? The gain, the question was to find gain. Let's see how we will do that. Okay, the first thing is to notice that this voltage VBE, okay, even if you are not 100% sure so far, just look at the simple logical argument that I am going to make here. VBE is simply the voltage division between R pi and 100 kilo ohms. So this voltage is supplied to two resistances, 100 kilo ohm and VBE. So the voltage VBE that applies across R pi, that appears across R pi, is simply voltage division. Okay, so that's what I'm doing, VI times VI. So VBE is simply voltage division. Now, once I have VBE, I should be able to calculate this guy. What is the reversing openings? I hope this horrible malady goes away sooner than later. It has possessed our beautiful earth for a long, long time. It is sending nations to despair. Okay, I hope this goes away soon. Now, V output in terms of the current flowing in here. Okay, so if there was a current of I flowing in here, I0, then what is the value for V output? V output is RC times I0, right? V output is RC times, that's Ohm's law. If there is a current of I0 flowing in here, there's a V output is RC times I0. But notice I0 is exactly same as negative I0 is exactly same as negative GM VBE, because the current that is flowing in this direction is opposite to the I0 current. So I can replace I0 with negative GM VBE. So V output is going to be negative GM VBE times RC. Okay, negative GM VBE times RC. Okay, now what you can do is you can notice that VBE can be replaced with all of this. Okay, I can replace VBE with all of that. So VOut can be expressed as negative GM times R pi over R pi plus 100 kilo ohms times VI times RC. Okay, now if you wanted to find the value of V output over VI, then all you have to do is the gain of this guy is negative GM R pi into RC over R pi plus 100 kilo ohms. Okay, that's all there is to it. It's a very simple problem based on voltage division and Ohm's law. Okay, let me see if I can make it, if I can put it in a different terms, if I can put it in a different perspective at all. Okay, so what we did earlier, we are familiar with this kind of problem. How would you find the overall gain when you have an intermediate gain stage? Remember, in the very beginning of the class, I gave you an idea, I gave you a notion in terms of what is your overall payout, okay, if you're investing into, I don't know, Apple or Tesla or Nikola, okay? So one of these companies, TSLA, what I mentioned that when you have a $100,000 that you want to invest, begin with, not all of that is going to appear at your investment as a stock for you. Some of that is going to be lost as a commission. Okay, so only small portion of your initial cash on hand is going to show up as stocks for you. Okay, so you can calculate that by cash on hand times the voltage division R pi over R pi plus 100 kilo ohms will give you the fraction of your cash that will appear as your investment. So when you look at VBE, the voltage over here, VBE, that's your actual investment. It's only a portion of it that shows up here. Then that portion of it, VBE, is actually multiplied by the gain of the Tesla stock. Okay, over time, the Tesla stock has multiplied 100-fold. Good for you. Okay, you started out with a small fraction of 100K, let's say 90K, because 10K was lost as a commission. That is multiplied by the gain of Tesla stock, which is 1,000. Okay, now what you have is 90,000 or 90 million investment. Okay, you have an investment of 90, you have a gain of 90 million that your 100,000 multiplied into. Okay, now you can cash that out right away here because there is no output resistance over here. If there was a commission on its way out, you would have to pay taxes and commission when you cash out. But here, all of the current that is flowing, that is coming over here, is actually, you can cash that out. Okay, you can, all the stocks that the value of the stocks can completely be taken out as your payout. That's why it shows up as V out. V output is the current GMVBE times RC. Notice if you pay attention to the direction carefully, it's going to be negative GMVBE times RC. So if you wanted to find out the overall gain, V out over V in, all you have to do is to replace this VBE with its equivalent. There is this V in term over here. Okay, you have to replace it with its equivalent R in term. Okay, so that's the idea of gain of an amplifier, something we discussed in the very beginning of the semester, right? So there's voltage division on its way in, commissions on its way in, and there may be commissions on the way, commission and taxes on the way out. That's all there is to it. Any analysis of any amplifier is based on this generalized procedure. Okay, and you can find out that when you plug in the numbers, negative GM VBE times negative GM VBE times RC was the gain. Negative GM VBE times RC is the gain. So I point something out to you. Okay, when you plug the numbers in, it's going to be negative 3 is the gain that you get. Okay, I'll point something out to you. The gain, okay, the gain really is a function of RC. Okay, the gain is a function of RC. Okay, if you increase the RC value, the gain is going to increase. Okay, the output voltage is going to increase. If you increase the RC value, the output voltage is going to increase for the same input. Therefore, your gain is going to go up. But is there a downside to that? Is there a disadvantage to increasing? Well, there is a disadvantage because if you keep increasing this RC value, okay, for the same IC current, for the same current, the voltage here is going to drop further, okay? Or in other words, with increasing value of RC, as you increase the value of RC, the voltage that you apply, that you get here is going to be very, very small. And therefore, the signal swing, that's going to eat into the signal swing of your output. So there is a trade-off that plays out between the signal swing and the gain. Okay, or in other words, at some point, not just the signal swing, if you make this resistance really, really large, okay, at some point, the voltage here, VC, is going to keep falling down so fast that it eventually is not reverse biased and it comes out of the active region. Okay, so you have to be careful that you're properly biasing with enough voltage headroom and legroom on VC, just so that even if your signal swing is large, you're not leaving this linear or active region of operation. Okay, there is a trade-off. All right, so that's the idea of small signal analysis. Okay, so here is the summary of key concepts: NPN and PNP are BJT device structures, and we looked at the symbols for those. There are different regions of operation: cutoff, forward active, saturation, and reverse active regions. Okay, in addition, we looked at the large signal model of BJT in the forward active region. Okay, We looked at that. We looked at some of the higher order effects, the base width modulation, lambda, okay, and other higher order effects, which are mostly inherited from the diode, second order effects. And then we looked at the DC biasing of BJT circuits and the small signal of BJT models, the small signal analysis of BJT models, using BJTs as voltage amplifiers. In this case, this is called a common source amplifier. Let me go back. Okay. Okay. Common emitter amplifier, the bread and butter gain stage. Okay. We talk about this in the next chapter. Where is the input? The input is between the base and emitter, right? Input is VBE. That is where, because that's where you're applying your input, right? Where is the output? The output is between the collector and ground, which is emitter, right? So this guy, V output is between collector and emitter, VCE. Okay, or if I'm paying attention to my VCE. Okay, input is on VBE, output is on VCE. So what terminal is common to both input and output? Well, no prizes for guessing. It's just emitter is common to both the input side and output side. It's called common emitter amplifier. And it turns out that CE amplifier for BJTs has very similar properties as common source amplifier for MOSFETs, and both of these are used as the bread and butter gain stage. Okay, when you want gain, you typically use common emitter stage or a common source amplifier stage. Okay, and then we look at different configurations of amplifiers in the next class. Questions, please. What questions do you have so far? All right, I want to stop here and I'll see you folks back around 12:15 for the lab.